Greetings, fellow colleagues of academia. Today, we will be presenting our submission to the 2020 Dynamic Data-Driven Application Systems Conference. My name is Joshua Darville, and I'm a doctoral student in the Department of Industrial and Systems Engineering at the University of Miami. I received my bachelor's degrees in both physics and mechanical engineering from Fisk University and Vanderbilt University, respectively. Currently, I'm working in the Simulation and Optimization Research Lab under the advisement of Dr. Celik. Today, we will be discussing the purpose of this research, why it is challenging, and the approach of other academics to this problem. We will delve further into our proposed solution and each component within it, as well as the results of this approach and future direction of this research. This outline has a few abbreviations that will be referenced throughout the presentation. Please take a few seconds to review. The motivation for this research is developing power grid systems which are resilient to extreme weather events and operate in a sustainable manner. The need for reliable energy becomes uncontroversial as the world deteriorates due to excessive use of fossil fuels. This global concern puts an immense strain on the power grid and economic activity, as the frequency of these climate catastrophes plaguing the world have increased according to recent statistics. Fires, hurricanes, and other natural disasters continue to affect millions of people daily. Despite this existential threat becoming a globally recognized concern, the rise in geopolitical tensions and the COVID-19 pandemic have compounded this problem. Thus, the world is becoming more decentralized, and it will be imperative for each actor to sustain themselves. The graph highlights the impact of these climate catastrophes throughout the economy, particularly in the power industry denoted by dark blue bars. Below is an example of the unnatural size of Dorian relative to the Bahamas, where the system stagnated for nearly 2 days before losing all of its energy. Grid resilience and cybersecurity are a must in the new economic landscape of the digital world and will be paramount to participate in free world markets, making a hurricane or a data breach akin to a US sanction. Previously, grid failures or blackouts were treated as nuisances to recreational activity over the internet. Now, an internet connection is essential for productivity, which amplifies the need to efficiently distribute energy while considering the existential threats of extreme climate events. Microgrids are subnetworks that can utilize distributed energy resources in parallel with the main grid to efficiently dispatch power, ensuring reliable distribution with quicker response times than their traditional manual counterparts. The general goal of a power dispatch model is to achieve the minimal cost of operation with the minimal amount of carbon emissions required to operate. Thus, dispatch policies tend to be multi-objective models where the objectives may conflict. There are a multitude of challenges when addressing sustainable power dispatch. There are challenges derived from the modeling of the physical power networks and challenges in achieving the optimal solution to dispatch control with limited computational resources in an appropriate time. However, rapid future computations incur an engineering trade-off between computational resources and the desired accuracy within an appropriate time, as the microgrid dispatch model scales. For large-scale bulk power systems, this approach becomes less applicable as the error rises for highly clustered load profiles or becomes too computationally expensive to solve the initial load profile. This dilemma presents both a challenge to reliable energy systems in times of crisis and an opportunity to utilize a load profile generated by the quarantine clusters for operational planning. Thus, understanding the parallel characteristics across various applications is crucial for innovation. Among the variety of clustering techniques, the most common is K-means, used on spatial data to aggregate similar load profiles and achieve accurate long-term load forecasts based on land use or location. However, other authors have clustered based on the user's load characteristics to reduce the complexity of communication between the grid and the users. Studies throughout the literature note the relationship between the scale of the microgrid dispatch model and the number of blocks that define its planning horizon. Studies throughout the literature note the relationship between the scale of the microgrid dispatch model and the number of blocks that define its planning horizon. Since this key finding is seemingly unanimous throughout the literature, the problem has been identified. Therefore, the challenge is then to obtain real-time situational awareness, which requires the regulation of large heterogeneous data for anomaly detection within the microgrid system. Consequently, the microgrid will need to steer instrumentation to acquire the most relevant sensory data at the appropriate fidelity for near real-time decision-making. The powerful paradigm, dynamic data-driven application systems, first introduced by Dr. DeRemo, approaches this challenge holistically. DDDAS equips the proposed framework with the ability to ascertain how the system and environmental data should be harvested as the microgrid simulation receives near real-time data from the microgrid system. In our submission, we focus on the challenge posed by the large solution space of dispatch control. The proposed framework in Figure 1 is segmented into 3 cycles and utilizes the symbiotic behavior between an executing application and the measurement data to develop a two-way feedback loop. Cycle 1 begins with the data received from the microgrid system and captures the microgrid simulation, the deviation clustering, and the rule-based policy modules. Initially, near real-time data from the microgrid system is fed into the microgrid simulation. The simulation produces the load profile according to the data received, which is then fed to the deviation clustering algorithm. After the deviation clustering algorithm processes the initial load profile, the newly clustered profile is then sent to the rule-based policy to determine the overall operational plan. Both the deviation clustering and the rule-based policy modules work in tandem to determine whether the next cycle should be 2 or 3. The microgrid dispatch model uses cycle 2 based on the previous publication with some extensions. Both cycle 2 and 3 are mutually exclusive, and the unselected cycle will become inactive. As cycle 1 recursively scrutinizes the data according to the rule-based policy, cycle 2 typically follows utilizing the microgrid dispatch model for decision-making unless the microgrid simulation receives anomalous data. In this case, cycle 3 would be chosen to involve some degree of the transmission system office's intervention. The DDDAS paradigm supports this symbiotic feedback loop, requesting information unique to potential anomalies while receiving near real-time data. This two-way communication feature of the paradigm helps to better mimic the real-world microgrid system by capturing the current system state and investigating extreme values to revise the current microgrid dispatch decisions. The microgrid simulation uses agent-based modeling to capture the individual behavior of each resource in the network. The agent-based models in the simulation were based on a previous publication, and encircled are the variables describing the external data subject to uncertainty. Common distributions throughout the literature describing the external data are listed on the right. The data was fitted with a tool in Python to obtain each factor's probability density function, box plot, and general statistics to give a macro overview of the data as seen in Table 1. The simulated load profile is filtered through the deviation clustering algorithm. This load estimation technique chronologically groups the initial load profile according to a tunable standard deviation for each subgroup and preserves its temporal characteristics. Deviation clustering addresses the large solution space challenge of dispatch control by reducing the model's dimension and consequently the planning horizon to the number of subgroups called blocks. A detailed description of the algorithm is presented in Table 2, and the effects of this estimation technique can be seen below in the graphs as the standard deviation is relaxed. The series of graphs below illustrate the effects of deviation clustering, where the red curve is the initial load profile and the blue curve is the resulting profile post-deviation clustering. The level of distortion can be visualized as the tuning parameter is relaxed. Two indicators are used to gauge the engineering trade-off between reducing the dispatch model scale and distorting the initial load profile when using deviation clustering. Both the indicator's definition and expression are presented. The resultant level of distortion is captured by the input error, and the resultant length of the planning horizon is captured by the block count simultaneously. Notably, this approach scales with the selected time step, although we plan for a day-ahead schedule. A schedule requiring a smaller time step is applicable. This allows for the realization of short-term microgrid operational planning. For example, a 1-minute schedule would contain 1,440 blocks, according to the equation. Hence, it is imperative to find a suitable sigma which effectively utilizes the computational resources during nominal operation. The graph in Figure 2 illustrates the trade-off between the indicators for one replication of the load profile as sigma is relaxed. The point of intersection between the indicators is where the trade-off ceases and is considered the limitation of this technique. Any further relaxation of the standard deviation would prioritize speed over accuracy, leading to useless results. Thus, the point of intersection is a data-driven reference to premise the rule-based policy and determine the overall operational plan. A single replication of the load profile was used, and the best sigma value was determined to be within the range of 0 to 30, which is up to the point of intersection. This interval reflects low to medium risk and gives preference toward accuracy as opposed to speed. Conversely, a high risk is associated with sigma values outside of the range of 0 to 30, which reflect a preference towards speed as opposed to accuracy. Designating the appropriate range based on the point of intersection updates the sigma value and subsequently the proposed deviation clustering and rule-based policy modules according to the most recent data. Additionally, this preferred region of operation can be adjusted before the point of intersection by the transmission system officer based on safety codes. Similar to the proposed framework, the proposed rule-based policy is segmented into 3 regions reflecting the level of abnormality associated with the data in that time step. Although the origin of the abnormality may be natural like the weather or unnatural like a system intrusion, the responses are predetermined in the loop previously captured by cycle 1. Thus, the rule-based policy is malleable and allows for triggered responses in unforeseen scenarios due to the randomness of external data. The transmission system officer can then designate regions based on their expertise and the required safety factor according to code. This dynamic property of the policy seamlessly integrates human oversight to the autonomous operation of the microgrid to compensate for the limitations of that automation. The transmission system officer can then steer the response towards low for autonomous operation or towards high and only supply critical loads while the anomalous data are being investigated. The courses of action associated with the abnormality levels are outlined, and a subset of the initial load profile reflecting public safety facilities called DCRIT remains energized despite any risk. The IEEE test network was selected as the testbed for replicability purposes. After collecting the data, the proposed approach for microgrid operational planning was applied to examine the effects of implementing the deviation clustering algorithm within a dynamic data-driven application systems framework. The microgrid dispatch model was based on our previous publication, but some extensions were added by introducing additional constraints from the literature. These additional constraints consider storage capabilities and frequency regulation during an unplanned islanding event. Moreover, the best compromise solution between these conflicting objectives of cost and emission were obtained with the epsilon constraint from this previous publication. 2 indicators are used to measure the performance of the proposed framework and its embedded modules. Both the indicator's definition and expression are presented. The speed ratio captures the efficiency gain from using deviation clustering, and the output error captures the cumulative error from both objective values within the dispatch model. The graph shows a reduction in solution time and the resulting efficiency gain indicated by the speed ratio. We observe a decrease in solution time at higher sigma values, which consequently enhances the execution speed of the microgrid simulation, reaffirming our previous observation. The speed ratio is defined as the solution time of traditional dispatch, where sigma would be 0, divided by the new solution time post-deviation clustering to capture any improvement. For example, a speed ratio of 2 at sigma equal 15 indicates that clustering at the sigma value results in obtaining a solution twice as fast compared to traditional dispatch. The sigma value is directly proportional to the speed ratio, which validates its use as a control parameter for clustering and consequently the scale of the microgrid dispatch model. The temporal characteristics of the initial load profile were retained at sigma equals 15, but not 60, since the input error increased from 3.7 to 35.2%. Moreover, the deviation clustering algorithm generates a solution 50% faster with a 3.7% risk at sigma equal 15 when compared to traditional forms of dispatch. It should be noted that this benefit of obtaining a solution time is limited by the level of risk incurred, which is reflected in Table 3 with increasing input error. The microgrid simulation's benefit of solution speed and limitation of distorted information using the deviation clustering module are summarized in Table 3. This allows for the transmission systems officer to determine an acceptable level of risk independent of the regions proposed by our rule-based policy module. The future work for this study consists of transitioning our deterministic look-ahead model to a robust optimization formulation that can search over a predetermined scenario set. Since our framework is based on a real-time application, the rule-based policy will adapt to accommodate conditions derived from the scenario set. The proposed dynamic data-driven application systems framework will remain applicable as individual modules are enhanced with additional functionality. Presented is a descriptive depiction on the left and a visual depiction on the right towards this goal. The relaxing assumption of this methodology is that the scenario set for our experiment is equivalent to the treatment combinations of a full factorial design. Since the factorial design is known to balance test points and has many variations, we use it as a basis for real-world scenarios. The quartiles of the box plot are the levels of each factor, and the likelihood is obtained from their probability density function. The table of analogous terminology summarizes the similarity between jargon used across these fields. Thank you all for your time and attention. This concludes our presentation. We hope this was insightful, and we will now be taking any questions you may have.